All right, so we're working with linear systems. So we have three equations. In general, we're going to have three equations, three variables. Usually, we will we'll use our variables x, y, and z, but they could be anything, a, b, c, anything. And what we want to do is we're going to do some operations, just like we did with two variable systems, and we want to transform our system of equations into a particular form. So we want to get it so that I'll just write an example up here. X minus y plus 2z equals 1. Y plus z equals 3. And z equals 2. When we have our system of equations written in a form like this, where we have all three variables in the first equation, we have two variables in the second equation, only one in the third equation. We call this row echelon form. And that's our goal, is to get our system of equations into row echelon form. And we didn't really talk about it that much when we were doing two variable systems, but this is exactly what we did when we did two variable systems. So we would, if we just had these bottom two equations, this is what we did when we solved by elimination. We eliminated one of the variables, and we have the solution for the other variable. And this one we have a little more work to do, because now I can take z equals 2 and plug it into this equation and get my value for y. And then I could get, once I get the value for y, I can plug y and z into this top equation and get our value for x. So we call that back substitution, when we substitute back into our equations to get our y and our x value. So our solution here would be -2, 1, 2. So z equals 2, y equals 1, x equals -2. So we call this is called an ordered triple instead of an ordered pair. And what we're talking about here, I'll show you some pictures towards the end. These three variable equations are equations of planes in 3D. So we're trying to find where planes intersect in 3D. So on the plane, two lines can intersect in a point or not intersect. It'll be the same line. In space, we could have three planes intersect at a point, and then some other things can happen because we have three planes and we're in three dimensions. And we'll talk about that in just a little bit. So some of our problems will say get your three variable system into row echelon form. That's what they mean, is to make it look like this with a stair-step pattern. And the procedure we're going to use is called Gaussian elimination. So that's the process we're going to use to get our system into row echelon form. It's named after Carl Friedrich Gauss, who developed the method. And when we use Gaussian elimination, we're going to do what we call row operations. And we just have three of them. And they're the same ones we use in two variable systems. So anytime we do a row operation, it doesn't change the solution to our system of equations. But we want to be able to write it in this more convenient form. So our row operations that we can do on a system of equations. We can exchange two rows. That doesn't change the solution. Sometimes it's more convenient to switch the order of your equations. So we can exchange two rows. We can multiply any of the equations by a constant. And we don't want our constant equal to 0. Because if we multiply a row by 0, we just end up with all zeros. And that doesn't help us out. And the third is the one that we're going to use most often, is we can add a multiple and I'm going to say add or subtract. I'm going to put subtract here. Usually we try to arrange it so we add. Add or subtract a multiple of one equation to another equation. And replace. So that's what we did. For example, when we did two-variable system, we multiplied 1 by 2 and 1 by -3, and we added them together, and we replaced one of the equations by what we got after we did that operation. So that's what we did when we did a two-variable system, and we're going to do that with a three-variable system as well. We just end up having to do it a few more times. So these are the steps we're going to use to solve these three-variable systems. So when we use these steps, when we do the row operation, it's called Gaussian elimination. We're solving a three-variable system by elimination, and we want to get our solution. So all I want to do today is go through a couple of examples of using Gaussian elimination on a system of equations, just to show you the steps that we use. All right, questions? Okay. So let's say we start with the system x minus 3y plus 2z equals 1, 2x minus 5y plus z equals -5, and 3x plus y minus 2z equals 1. So there's our system of equations. I'm going to make all the steps explicit here. You don't have to write out all of this as you're doing this. I just want to make all of everything that we're doing explicit. So I'm going to label my equations 1, 2, and 3. Now usually with Gaussian elimination, what you want to do is use the first two equations to get rid of this part. Use the first and the third equation to get rid of that part. And then we'll use what's left to get rid of one of the y's. So whenever we this first equation, it's fine. So after our next step, it's going to stay the same. But what are we going to do with the first and the second equation to get rid of this 2x? What can we multiply one or the other by, so when we add them together, that 2x goes away? Just like we did in two-variable systems. What would we do? Multiply the first one by -2, and then add them together. So I'm going to write this. So we're going to multiply 1 by -2, add to 2. And that's going to be our new second equation. So remember in the row operation, it says we add these together and we replace. So when I multiply this by -2, I get a -2x plus 2x, I get a 0x. I get -2 times 3y is 6y minus 5y. So I get a y. And I get a -4z when I multiply by -2, plus z is -3z. And a -2 minus 5 is a -7. So now I've gotten rid of that x. What am I going to do for the first and the third equation to get rid of that 3x? multiply the top one, the first equation, by negative 3. So I'm going to multiply 1 by negative 3, add to 3. And that's going to be my new third equation. I'm going to replace the third equation by whatever I get from that. So I get a negative 3x plus 3x, so I get a 0x. I get a negative 3 times negative 3, so 9y. 9y plus y, so I get a 10y. Negative 3 here, so I get a minus 6z minus 2z, so minus 8z. Multiplied by negative 3, so I get a negative 3 plus 1 is, and this should be, sorry, this should be a negative 1 here in order for it to work out the way I want. So negative 3 minus 1 is negative 4. So that's my new system of equations that has the same solution as the original system of equations. I did row operations. This system of equations has the same solution as this system of equations. But we got rid of those x's. Now we're going to use equations 2 and 3 to get rid of these y's. So how am I going to get rid of those y's with equations 2 and 3? Doing the same thing that I did with these two. I'm just working with these equations, just working with those two. So what am I going to do? Multiply 2 by, by negative 10. Multiply 2 by negative 10. And when I add those, that'll get rid of that y. So I'm going to multiply 2 by negative 10 and add to 3. So my first two equations are going to stay the same. So my new system is going to be this. I get a y minus 3z equals negative 7. And now I'm going to have a new third equation. So when I multiply 2 by negative 10 and add, I get a 0y. I get a 30z minus 8z, so I get a 22z. And I get a negative 70, sorry, positive 70 plus negative 4, so I get a 66. And we're almost there. This is not quite in row echelon form. What do I need to do to get it into row echelon form? I need the z by itself. So how can I get the z by itself in that last equation? Divide by 22. So in row echelon form, that system of equations would be x minus 3y plus 2z equals 1. Y minus 3z equals 7, and z equals 3. This is a minus 7. There's my row echelon form. I know z equals 3. I can back substitute to get y, and then I back substitute y and z here to get x. My solution is the point 1, 2, 3. So solving by Gaussian elimination, we just follow this procedure until we get our system of equations to look like this. Questions on that example? Now, the important thing to remember as we do these operations, when we multiply one by a number and add to another equation, we're replacing one of the equations with the result that we get. So we want to be able to simplify our system, so we're always replacing one of the equations by our result. I could, if I wanted to, when I multiply 1 by negative 2, I could rewrite this equation multiplied by negative 2, and then rewrite this equation, the second equation, multiplied by negative 10. But the row operations say that the solutions are the same. So we don't have to rewrite them multiplied by negative 2. We can do that operation and then replace the other row, so we don't have to keep making these numbers get bigger and bigger and bigger. We could, but we don't have to. So these three planes in space would intersect at one point. All right, we good there? All right, so I want to step through one more example where something a little different happens with our solution, and then talk about the possibilities for solutions. All right, so here is our system here. X plus y plus z equals 2. 2x plus 3y plus 4z equals 5. And x minus z equals 1. All right, so if I would have started out with this system and this third equation were in a different place, I would put it in this last row because it's missing the y there. So you can always exchange the rows so that one's in a convenient place. We know that in our last row we want to have a z by itself. So here part of our work is already done. So I'm going to do the same thing that I did before. Call that equation 1, equation 2, and equation 3. The first equation stays the same, x plus y plus z equals 2. So how are we going to get rid of this 2x between these two equations? We want to get rid of that 2x. Multiply one by, what are we going to do? Multiply the first equation by negative 2. And we're going to add to 2. So our new second equation, we get a 0x, we get a negative 2y plus 3y, so a y. I get a negative 2z plus 4z, so I get a 2z. And I get a negative 4 plus 5, get a 1 there. And then to get rid of this x, I'm going to multiply the first row by negative 1 and add to 3. So I get rid of, to get rid of this x. So multiply the first row by negative 1, I get a 0x, I get a minus y plus 0y, so I get minus y, a minus z, so minus 2z, and a minus 2 plus 1, so I get a 1 there. Negative 2, so I get a negative 1. All right, so now I want to get rid of, did I make an arithmetic error here? Negative y minus 2z, no, we're good. So I got rid of this x here. How do I get rid of this y? What do I do to these two equations to get rid of this y? Since I have a positive here and a negative there, what do I do to them? Just add them together. And remember, we're replacing the third row by what we get when we add them together. So I'm going to add 2 and 3. So my first two rows are x plus y plus z equals 2. Y plus 2z equals 1. And my new third row, when I add these together, I get 0 equals 0. So when I add these together, I get 0 and 0. What does that tell us? An infinite number of solutions. So just like with a two-variable system, when you get something like 0 equals 0, 1 equals 1, 5 equals 5, something like that, we have an infinite number of solutions. And because we're talking about three planes intersecting, it's a little more complicated than it is when we're talking about lines intersecting. And I'll show you some pictures in just a second. So this gives us an infinite number of solutions. Two planes intersect in a line. So these planes could intersect in a line, they could intersect in 2 lines, or they could end up intersecting in 3 lines. But we can just say that it's infinite number of solutions. We won't have to find what the lines are here. And if we got an answer like 0 equals 5, what would that tell us? No solution. And if we have 3 planes and we're trying to find where they intersect and we get no solution, what's that tell us about the planes? They're parallel. So a picture of how this could happen. So here's no solutions. Here's one solution. Those planes are intersecting right there at that point, where the red, the green, and the yellow plane come together. But we can get an infinite number of solutions if the planes intersect like so. We would get a line where they intersect. We could have 2 parallel planes and a 3rd plane intersecting them, so we could end up with 2 lines where they intersect in pairs. Or they can make kind of this triangle shape, and we could end up with 3 lines where they intersect in pairs. So infinite number of solutions is a little more complicated in 3 dimensions than it is in 2 dimensions. But these are our possibilities. All right, so questions on row operations using Gaussian elimination. Okay. Homework. All right, there we go. Some of these problems